Hi everyone, welcome back to Statistics and Data Analysis. Today we're going to talk about distributions and sampling. So in previous lectures we have learned about two separate topics. One is about descriptive statistics. Okay, we spent a few weeks talking about how may we look at existing data and visualize and summarize some facts of the data. So we're talking about some actions we do for existing data. On the other hand, we studied probability. There we consider some assumed probability distributions or some hypothesized probability distributions and calculate the expectation or do some inventory optimization stuff and so on. So these two things are somewhat different, one from the facts and one from the theory. Now it's time to connect them. Today we're going to talk about how may we estimate the distribution of a random variable from existing data. Okay, so we're going to look at some simple outcomes and use that to find the assumed probability distributions. So that's one thing. Moreover, we want to study when we do sampling, what are some possibilities. And what's the most important is that we want to talk about sampling distribution, which is the probability distribution of something collected from the sample. Okay, only with that knowledge we can infer the population. So that's my plan today. Okay, so the first first two videos will be talking about how to estimate the probability distribution of a given random variable. And then we will spend some time to talk about sampling techniques, sample means, and the distribution of sample means. Okay, so let's start. Now I want to do one thing. I know something is random and I want to estimate its probability distribution. Okay? Last time we said we were given a probability distribution and then we do this, do that. Now we want to estimate the probability distribution. So some examples are, given a population of people, what will be the age of a randomly selected person? Now, that may be random. Given a potential customer, will he or she buy my product? That's random. Given a web page and a time horizon, how many visitors will we have? Or given a batch of products, how many will pass a given quality standard? All of them are somewhat hidden or random. So we want to do some estimation about the distributions of the random variables, which means for each possible value of that random variable, I want to know how likely it will be realized. Okay, that's basically the definition of a distribution. So to do that, of course, we need to have some data. So we need to either do experiments to get data or to run the operations and collect historical data. In either way, we can go from an observed data set to a probability distribution. Okay, so let's formalize our idea with the following formula and examples. So I'm saying that I have a random variable and I want to know its probability distribution. More clearly or more precisely, if I have a random variable capital X, I want to find its CDF, which is the probability for capital X to be less than or equal to any given level. If I can know the CDF, then I have a full picture of the random variable or random event. Okay, so you probably want to ask, why do we want CDF? Why not PDF or why not probability distribution? Well, the answer is simple. Because we do have two categories. One are discrete random variables. In that case, we have probability functions. Or we have continuous random variables. There we have PDF. Okay, so it's not so easy to say we want this or that. But for both types of random variables, we both have CDF. So that's why we say, oh, I want a CDF. Okay, so a problem may be like this. I have a coin. I want to know whether it is fair. The question about whether it is fair is actually asking about its distribution. Why is that? Suppose I say x is the outcome of tossing a coin. Then I can say, oh, x have two possible values. Either I say it's 1, then which means a head, or 0, which means a tail. Then what I want is this probability distribution. Okay? I say the probability for x to be 1 is p, which is 1 minus the probability for x to be 0. Then answering whether it is fair is to answer or to estimate whether p is exactly 1/2. If p is greater than or less than 1/2, then the coin is not really fair. Okay, so if I give you a coin and ask you that question, obviously we will do experiments. Okay, and once we do that, we're going to calculate or to count the frequency distribution and to use that as our estimated probability distribution. What does that mean? I'm going to flip the coin for maybe 100 times or 1000 times, whatever. And in that case, I'm going to count for what proportion of trials I get a head and for what probability I get a tail. Okay? For example, if I get 46 heads out of 100 trials, I'm going to estimate that P is 46%. Okay, that's something I can do. Of course, we know, well, that's not perfect, right? Because the frequency distribution and the probability distribution obviously are different. Frequency distribution is according to a sample, according to the outcome of some past data, according to the outcome of some experiments. So it's something we observe. On the other hand, the probability distribution is something that we want to guess or we want to estimate. It is a property of a population, and we have no way to exactly know what it is. So all we can do is to use the frequency distribution to approximately estimate the probability distribution. And we all know that that estimation would be better if we have more trials or more data. Like here, if I do it for 100 times, then I may get some error, obviously. But if I do it for 1,000 times, 10,000 times, or 1 million times, then this procedure would give me a better estimation in expectation. Okay, so that's basically the idea. So now that idea can, of course, can be generalized. Like there are some kind of random variables, they are still discrete, but the number of possible values are more than 2, but not too many. Okay, then in that case, if we say x is the random variable and capital S is the sample space, then capital S contains some discrete values, but there are the number of possible values are not too many, maybe 5, maybe 10, or typically do not be more than 15 or 20. In that case, we're going to estimate this probability function, because if we have that for all the values, then we also have the CDF, right? Then just like the coin tossing example, now we can still do the same thing and count the number of observations of each value, and then we just use the proportion to do the estimation. The formula is here. Suppose I collect past data or do experiments and get n outcomes, x1, x2 up to xn. This is our sample data set. And then I'm going to count the number of trials where I get x and use that as the numerator divided by the total number of trials I have. So that's simply the proportion, right? And I'm going to use that proportion to be my estimated probability for that value to happen. And of course, after that, sometimes we need to do some manual adjustment. Okay, so let's see an example. A data set records the daily weather for the 731 days in 2 years. So that's very familiar to all of us, right? 1 means sunny day, 2 means misty and cloudy, 3 means light snow or light rain, and 4 means a very bad situation. So suppose I say X is the daily weather for a future day. Then our sample space has only 4 values, 1, 2, 3, and 4. So that's not too many. Then all we need to do to estimate the distribution of X is just to look at the historical data set. Okay? In total, I have 471 days, and I see among that 731 days, I have 463 days that has a sunny day. In that case, the proportion is about 63%, and so on and so on and so on. So after I take a look at all those 731 days, I'm going to make this conclusion or make this estimation. I'm going to one thing I can do is to say, okay, according to the historical data, I'm going to guess that P1 is around 63%, P2 is around 34%, and so on and so on. Okay, that's some estimation I do according to historical data. And I don't need to really do a lot of weird things. All I need to do is to count the proportions. Okay, I of course know that this estimation is just based on a sample, so we know it's never right, but it's intuitive and easy to implement. Okay, and if the data set is large enough, if the sample data set is large enough, then this method would be good enough. In any case, we may want to do some manual adjustments based on experience or knowledge. Okay, like today, I'm thinking about what's going to happen for the one day in the future. And I know even though in the past 2 years there was no snowy day, but that does not mean in the future it's not going to happen, right? And probably I need to have a positive probability for a snowy day so that I can prepare for that. In that case, I say, okay, I want to be conservative so that I want to give a positive probability to 4. Okay, in that case, I can always do some adjustment and say that, okay, I'm going to do this. I'm going to set P1 to be 65%, P2 to be 30%, P3 to be 3%, and P4 to be 2%. So I can do the manual adjustment. And whether that adjustment makes sense or is helpful or not depends on human judgment, depends on the domain knowledge, expertise. Okay, then that's beyond statistics. But before that, you will do data analysis and get this as a reference for you to do manual adjustments. Thank you.